Uh, let's now extend on this idea of roots and coefficients in polynomials. So a reminder of what we've seen. We ended up generalising for any polynomial, you might remember. And we said, well, look, sum of the roots one at a time, and again, it doesn't matter, it could be a quadratic, it could be a cubic, and so on, will always be minus b on a. 2 at a time will then be positive c on a. 3 at a time, minus d on a. And we can keep going in that sort of pattern, depending, of course, on how many coefficients and how many roots we have. This idea for quadratics we saw, alpha squared plus beta squared, basically just the rearrangement of the perfect square formula. But we also saw, and that was a common one as well, when we have algebraic fractions. We turn it into one fraction, and the denominator will then usually become product of the roots, and the numerator the sum of some sort, 1 at a time, 2 at a time, depending on what the original denominator was. But as I said, these can also be generalised in that it will always be the sum of the roots squared will be the sum of the roots 1 at a time, all squared, minus 2 times the sum of the roots 2 at a time. So we can always use that pattern. When it comes to the standard algebraic fraction question, it's a bit hard to generalise, but the sum of the roots 1 at a time, well, if it's order of 2, then we get sum of the roots 1 at a time over product of the roots. If it's order 3, we get sum of the roots 2 at a time on product of the roots. If it was order 4, we get sum of the roots 3 at a time over product of the roots. See, we can see there is some sort of pattern there. Yeah. Well, the order of the polynomial. So if that was for a quadratic, you'd have 2 roots, and so you'd end up with that and so on. Yeah. Okay, so here's a cubic. Often they'll ask us to find the 3 basic ones first. There's your gift marks if they do. Of course, even if they don't ask us, we're probably going to have to find them anyway. So 1 at a time for this one is 2, 2 at a time is 3, 4, just a nice pattern there. But that's kind of appropriate given today's date when you think about it. Sum of the roots squared then. So as I say, we can generalise that one. It'll be the sum of the roots 1 at a time all squared minus 2 times the sum of the roots 2 at a time. So subbing in what we've already found, we get our answer, -2. Straight away, that tells me something about the roots of this cubic. Yeah, we're going to have a couple of complex roots, because how can you add up squares and get a negative number? Now, it is a cubic, so there must be one real. So straight away, I know now, for this particular cubic, if I was to draw it, it would have one x-intercept. As far as the roots or the zeros go, it will have one real one, 2 imaginary ones. Sum of the roots cubed. Now, I could generate a formula like I did here, but there is an easier way. If you think of each root by itself, if it's a root, we know it satisfies the equation. So it must be true that alpha cubed minus 2 alpha squared plus 3 alpha minus 4 is equal to 0. But that is also true for beta, and it's also true for gamma. If I treat that as 3 simultaneous equations, I end up with the sum of the roots cubed minus 2 times the sum of the roots squared plus 3 times the sum of the roots minus 12. So basically it mimics the actual equation. The only thing we have to be careful with, of course, is the constant at the end. I don't have minus 4. I have minus 12 because that constant is there for each of the roots. So I get 3 lots of them. Now I can sub into this formula. Well, I might rearrange it first. I can sub into that formula and find out the sum of the roots cubed. And there's our answer, 2. Wow, they all seem to be 2 or minus 2. So if I then had to find the sum of the roots to the power of 4, okay. Remember, we wrote down that alpha cubed minus 2 alpha squared plus 3 alpha minus 4 was equal to 0. And we know that to be true. Well, it's just an equation. So whatever I do to one side, I do to the other. So if I multiply both sides by alpha, the right-hand side is still going to be 0. But the left-hand side, I now have alpha to the power of 4 minus 2 alpha cubed plus 3 alpha squared minus 4 alpha equals 0. Well, that's alpha. Could have done that for beta, could have done that for gamma. And so like I just did in the last one, we could create a simultaneous equation. Again, notice it matches the pattern of the equation. It's just that every power in the original equation, if you like, has been increased by 1. And in this one now, because I've increased the power by 1, the constant is not 12. It goes back to being the regular minus 4. So we could find any power. All I've got to do is mimic the equation and just add on the appropriate number to the power that I need. So if they wanted alpha to the power of 5, then I could write down, oh, well, I know that's going to be sigma alpha 5 minus 2 times sigma alpha 4 plus 3 times sigma alpha cubed minus 4 times sigma alpha squared. It just mimics the actual equation. But the one drawback, of course, is in order to work out alpha to the power of 4, I'm going to need to know alpha cubed and I'm going to need to know alpha squared. But of course, we have worked those out already, so we can just substitute in and we get 18. Okay. So powers above 2, basically we try and mimic the actual equation. Right, alpha plus beta times alpha plus gamma plus beta, times beta plus gamma. The temptation is to expand the whole thing out. And I will end up doing that. But I don't want to have pronumerals everywhere. So I'm actually going to rewrite it. And I'm going to say alpha plus beta is actually the sum of the roots one at a time minus gamma. And alpha plus gamma is the sum of the roots one at a time minus beta. And so on. Why do I do that? Is because I can replace that now with a number. Now I'm still going to have to expand the whole thing out. But instead of having a whole heap of pronumerals, I'm going to reduce the number of places I actually have to substitute into because I'm now just using a number 2. So when I do expand the whole thing out and then group the things together, you'll notice I get 8 minus 4 times the sum of the roots 1 at a time, 2 times the sum of the roots 2 at a time, and then minus the sum of the roots 3 at a time. As I say, if you had expanded the original one out, you should still end up with the same answer, which, once again, it's 2. But I don't know, I just find that easier myself, so I don't have so many pronumerals flying around everywhere. Ooh, one from a paper, 1996. So it's a quartic, it's monic. So this is where we've got to be careful, because when we say minus b on a, it's actually a on 1 and things like that. Just be careful. But we're told they're all integers, so we know that we've got whole number coefficients. The equation has a root of the form ki, and k is real, doesn't necessarily have to be a whole number, it's just a real number, but it's not equal to 0. Well, that makes sense because 0 can't be a root of this. If we substituted in, we wouldn't get a correct answer. First part, here's the gift mark of the question, I guess. State why the conjugate minus ki is also a root. So they're just looking for that you understand, hey, if all the coefficients are real, then I know that the imaginary solutions will appear in conjugate pairs. That's all they're really looking for. So something like that. So that's exactly what I wrote, really. Roots appear in conjugate pairs when the coefficients are real. All right, they want us to show that C is equal to K squared A. Where to begin? So many things you could try. I mean, I could substitute in Ki, because I know that's a solution. I could substitute minus Ki in as well, because we now know that's a solution as well. I could play around with the roots. I have factorised it to be x plus Ki, x minus Ki. And I suppose my logic when I originally wrote this question out is that, hey, why did they get me to do part A? Like, what were they trying to tell me? So I suppose that's why I went this way with part B. And that I thought, well, there must have been a reason why they've pointed out this thing about Ki and minus Ki. So I've made them a factor and then said, All right, it'll be times some quadratic because I know it's a quartic. Then I expanded the whole thing out. Wow. And then I'm going to use the idea we saw back in quadratics. Remember quadratic identities where we said the coefficient of x squared is equal to the coefficient of x squared and so on? Well, that's true for all polynomials. So I'm going to do the same here and say, all right, well, I now know that the coefficient of x cubed must equal the coefficient of x cubed. So p is equal to a. And coefficient of x squared is equal to coefficient of x squared. So q plus k squared is b, and so on. So I've now come up with 4 equations. Now, I might not need to use them all. We're trying to show that c is k squared a. Yeah, I can see. Can you see it straight away? We've got the first one here that simply says p equals a. And if you have a look at the third one, we've got k squared p is equal to c. So I can simply substitute the first one into the third one, and we get our k squared a is equal to c. Okay. Now they want us to show that c squared plus a squared d is equal to abc. Okay, so this time I've used the second equation and rewritten it there. So q is equal to b minus k squared. Sub that into the fourth one, and I get k squared outside of b minus k squared is d. So bk squared minus k to the power of 4 is equal to d. So substituting that in, actually I've substituted it in for k squared, but we end up k squared. When I rearrange what we just found, we'll get k squared as c squared on a squared. So that's what I've used there. Sorry, k squared is c on a. All right, I now have something that just has b's, c's, a's and d's. So it should be possible to rearrange this to get the expression that they want. So I suppose let's get rid of the fraction. Multiply everything by a squared, and we get abc minus c squared is a squared d. And that's pretty much it. We just need to move some terms around, and we've got what they want. C squared plus a squared d is abc. All right, if 2 is also a root of the equation and b is equal to 0, show that c is even. Okay, so what do we know? We know ki is a root. We know minus ki is a root. We now know 2 is a root. So there is a fourth root that we don't know. I'm just going to call it alpha. Okay, so I don't know what that root is yet. Now, here's my logic. As the other 3 roots, the 3 roots that we know are integer multiples, and the product of the roots is an integer, alpha therefore must be an integer. Okay? So I know alpha is an integer. Whether that's useful or not, I don't know yet, but I've got it in my head, alpha is going to be an integer. So I'm now looking at the sum of the roots 2 at a time. Okay. Well, let's tidy that up, because look, we've got where our conjugates have both been multiplied by 2, so they'll cancel each other out. Same with the alpha ones, they'll cancel each other out. So I end up with k squared plus 2a is equal to 0. We're trying to show c is even. Okay, so k squared is minus 2 alpha. K squared is minus 2 alpha. But, let me just redo that. Remember we said c was equal to k squared a. So I can now say c is equal to minus 2 alpha times a. Remember, a is an integer, alpha is an integer, so I'm saying c is 2 times some integer. Well, that makes it an even number. So it's 2 times something. It certainly has a factor of 2. So as everything else are integers, m is also an integer. C must be an even number, so it's divisible by 2. So that's how I approached that particular one there. All right. In our Patel this time, so we'll look at 5D. We've got some questions there to to have a look at.